The final question on this test was again a free body diagram question. There was a bit of a theme to this test. In this free body diagram question, it was a question about dynamics, so the sum of the forces was equal to mass times acceleration, so there was a non-zero acceleration in this problem. So we have a person standing on a scale. The scale's on some kind of ramp that is accelerating the scale upwards at 1 meter per second squared. This ramp is inclined at an angle 20 degrees above the horizontal. Person doesn't slip. The scale doesn't slip. The person has a coefficient of friction with the scale of 0.8. In the first part, we're asked to draw a free body diagram for the forces acting on the person, labeling each force, and here's some examples of possible types of forces, how we would label them, with subscripts indicating the two interacting objects. We're asked to use E for the earth, R for the ramp if we use it, S for the scale, and we should use P for the person, presumably. So the first step is to think about, well, what kind of coordinate system do we want if we have an acceleration up the ramp? It's useful to use a tilted coordinate system where one of the directions is the direction of the acceleration. So here's our tilted coordinate system. Let's choose x to be the direction up the ramp, y to be the normal direction to the ramp. And now we have to draw a free body diagram for the forces acting on the person. We should right away say, well, there must be a net force acting. The sum of these forces has to add up to something that's causing that acceleration up the ramp. We represent our person as a dot. We represent their weight as a vector going directly down. And the angle that this weight is making with respect to the y-axis is 20 degrees, which we can pick up from that angle, noticing that it would form a right angle triangle with this. That would be 70 degrees, and so to make a right angle on our new coordinate system, it has to be 20 degrees. There. Now, what is accelerating this person up the ramp? Well, there must be a force that's doing it. It's a force that's acting between the scale and the person. And we're told that this person is not moving relative to, does not slip, means that the person is not moving relative to the ramp. So they're at rest relative to the, they're not moving relative to the scale. So they're at rest relative to the scale. So there's a static force of friction that is causing this person to accelerate up the ramp. So static force of friction, and this is a force due to the scale acting on the person. So scale on person. And the weight, of course, is the earth acting on person. So E on P. The other force that we have here is the force that's stopping the person from going through the scale, and that's the normal force, and that should be equal in magnitude to the y component of our weight. Here's our normal force, and again, this is a force that's a contact interaction between the scale and the person. So there's our free body diagram. There's our free body diagram. Oh, it's so fun to do things off the camera. So let's describe those things again, since some of them were off the camera. When we start our free body diagram, we draw our net force up the slope. We draw a dot at the center of our free body diagram once we've labeled x and y axes. The weight points directly down. We recognize that this angle is the same angle as the angle that we're given, based on this angle being 70 degrees. So we put 20 degrees there. We recognize that the only force acting in the direction of acceleration here is the static force of friction, which is tending to keep this person at rest relative to the scale. And then we put a normal force directly upward on the person, which is stopping the person from going through the scale. The subscripts on our forces, this is S for static, S for scale, acting on P for person. This is E for Earth, acting on person. So the Earth is has a long-range force of gravity acting on the person, and the normal force comes from the scale acting on the person. Now that we have our free body diagram, we can write Newton's second law in component form. So to do that, we know that we have to write the sum of the forces in the x direction is equal to mass times the acceleration. We've chosen our acceleration to be pointing along the x direction. The only force in the positive x direction is the static force of friction. We're going to drop the subscripts for now. The only force acting in the negative x direction is the weight, which only has a component of its force acting in that direction. So this is the weight times, going back to our diagram, the component of the x-axis component is the sine of 20 degrees times the magnitude of that weight. So we put in sine of 20 degrees. And this weight is the mass of the person times g. That's one of our two Newton's second law equations. Our second equation is sum of the forces is in the y direction. Well, there's no acceleration in that direction, according to our free body diagram, so that's equal to 0. The normal force is pointing directly along that direction in the positive y-axis. And there's a component of the weight which is pointing in the negative y-axis. So weight times a cosine of 20 degrees. Again, weight is the mass of the person times g. So now we have two equations. We'd like to solve them for the reading on the scale. The person's apparent weight. The reading on the scale, again, is the normal force that's pushing up on the person. We've got a normal force here. So normal force, take away weight, mpg, times a cosine of 20 degrees is equal to 0. So putting the weight on the other side, normal force is equal to substituting in for the mass of the person, which was a 100 kilogram person on the group test. So we put in 100 kilograms times 9.8 meters per second squared times a cosine of 20 degrees. Bring out our calculator at this point. 20 degrees cosine times 9.8 times 100. And so on the group test, the normal force was 921 newtons, and that's the reading on the scale. And now we need to find the size of the frictional force acting on the person. And so we're going to use our other equation. Size of the frictional force acting on the person is F sub s. So F sub s from that equation is equal to mass times acceleration plus the weight of the person times the sine of 20 degrees. And so we can plug in mass of the person is 100 kilograms. Acceleration of the person is 1 meter per second squared. Again, mass of the person is 100 kilograms. G is 9.8 meters per second squared. And the sine of 20 degrees. So let's put all those things together. 100 times 1 plus 100 times 9.8 times 20 sine equals So for the group test, we find 435 newtons is the static frictional force. Now, whenever we do a problem like this, we have to make sure that the static frictional force is an allowed static friction force. Otherwise, the object isn't at rest. So let's make sure the object is actually at rest relative to the scale. We require, for that to be true, for the static friction force to be less than or equal to mu s times n, which is the static frictional force's maximum value. So this is 0.8 times the normal force at 21 newtons. That's what we saw for in part C. And we see that 0.8 times 921 is equal to 737 newtons. And so this is okay. It is the static force of friction is less than the maximum static force of friction, and so we're done.